Plate tectonics theory arose from a tradition that believes big changes occur very slowly over long periods of time. But there is another way to look at dividing the continents, as a sudden catastrophic event. Look beneath the fire and ash. I'm Mike Fisher, introducing you to a theory I call shock dynamics. Since the mid-1960s, researchers have recognized that sections of Earth's crust have moved apart. Shock dynamics theory is founded on an additional observation, that moving continents went directly away from the very same spot. In plate tectonics, deeply hidden forces such as rising plumes, churning cells, and diving plates are imagined to be driving all the pieces of crust. In shock dynamics, an explosion sends continents sliding over crust like ships on water. As molten rock hardens, it records the surrounding magnetic field orientation, and this paleomagnetism has been used to estimate where land masses were in the past. But Earth's magnetic field may well have reeled about for an extended period of time after a giant meteorite impact. This would not be much use as a frame of reference. More reliably, we can reconstruct the protocontinent by using mid-ocean ridges and other geologic clues. And this is what we get. The blue here is oceanic crust, not water, and the brown on top of it is continental crust. Oceanic crust averages over 4 miles thick, while continental crust averages 20 miles thick. Now, considering only the densest so-called iron meteoroids, small ones may burn up in the atmosphere, or form the familiar bowl-shaped crater if they strike the Earth. Large meteorites explode and form a bowl-shaped crater whose floor collapses upward into a flat basin with a central peak or ring. The giant meteorite powering shock dynamics vaporized a 500-mile-wide hole in the continental crust. Shock from the explosion pushed outward in all directions. A typical feature of lower-angle impacts, say 20 to 45 degrees, is side blowouts. That effect appears to have initiated the split along the east coast of Africa. What do we find at ground zero? This image from the Sandwell satellite altimetry map shows the central peak of the complex crater, the Aldabra Islands. Around the crater, shown in yellow here, pressure from the impact pushed magma to the surface. It formed the Comoro Islands, the Mascarene Plateau, the Kenya Dome, and Mount Kilimanjaro, a triple volcano and the highest point in Africa. Explosive shock also buckled East Africa and made the small Amarante Trench in oceanic crust at the crater's edge. As the Americas drew away from Africa, they pulled open the 2,000-mile-long East African Rift. The last feature near ground zero is a piece of continental crust in the Seychelles. In the same way that force from this mallet passes through the blue ball to move the red one, force from the impact explosion passed through Africa, Madagascar, and the Seychelles to move the pieces beyond them. This paradigm suggests new causes for crustal features outside of ground zero. What I call impulse mountains are the low-folded ranges that result from the push that starts a landmass moving. Examples of this are in North America, South America, and Australia. Continents are too huge to experiment with, but we have some clues about how they react to force. The collision with India pushed up mountains all the way to Siberia rather than just at the point of contact, indicating the continent is loosely attached to the crust below it. H.J. Melosh has proposed that the crust behaves as a Bingham fluid, which is a solid until applied stress exceeds its cohesion. Then it flows like a fluid until shear stress falls below the cohesion and it suddenly becomes solid again. His first example is the fluidizing and sudden freezing of a complex crater. Next is earthquake slip, which produces almost none of the expected heat from friction. Third are landslides. Small ones end up near where they fall, but large volume ones have slid up to 30 times the distance they fell and are called long run-out landslides. The critical factor seems to be thickness. What if a continent behaves like a long run-out landslide when it begins to move? Forward motion and overlying weight fluidizes the base with acoustic energy. As forward momentum gradually slows, fluidization at the leading edge decreases. Friction increases along the leading edge, and the momentum of the continent piles up massive mountains until everything stops. I call these break mountains. Because the protocontinent was shattered, most pieces flew apart. However, Alaska hit North America, and the Indian bloc struck Asia to form collision mountains. This model shows how the collision turned Asia and raised break mountains in southern Europe. The event left scars in the oceanic crust. The low-angle impact apparently launched a crustal wave eastward. Crust was temporarily fluidized behind the front and froze as a cresting wave, forming the Tonga and Mariana Trenches. In the same way that a turning boat kicks out a curved or arced wave, small pieces of continental crust appear to have kicked out what I call arc trenches. Quite different are simple cuts I call gouge trenches. In shock dynamics, mid-ocean ridges and their transverse fractures formed as a thin skin over melted crust, drawn out between separating continents. Surface melting occurred when the weight of continents moved off of oceanic crust. Today, Earth is like an egg with a cracked shell, pulled in all directions by members of the solar system. This causes slight crustal motion and earthquakes. Now, to put it all together, take a look at the event from 6 different points of view and witness the extraordinary explanatory power of this theory. It appears that there were already 2 large complex craters in North America before the giant meteorite hit. Though Hudson Bay was opened up during North America's move, their forms can still be seen. Impulse mountains formed as North America was pushed off of Africa. Central America unfolded from between North and South America. Greenland and the northern Canadian islands broke off of North America as it moved. An arc trench formed as the Antilles pulled off of South America. Break mountains along the entire leading edge stopped all movement. Again, East Antarctica was an island below the protocontinent. As it was pulled away, it opened a gash and outflowed the Kerguelen Plateau. Again, as the bloc consisting of Australia, India, and Southeast Asia slammed into Asia, Europe was being pulled away by North America. The crustal wave, shown here in blue, is actually beneath the continents. The collision with Asia shattered the block and built collision mountains. The crustal wave split into two parts. The collision sent Australia careening eastward. As Asia moved north, more mountains grew and Japan was thrown outward, trailing an arc trench. Momentum drove India and Southeast Asia deeper into Asia, causing China to be pushed out. Asia pivoted counterclockwise, driving Europe down. Break mountains stopped Europe, and brief compression formed the Ural Mountains. Again, Europe was originally sandwiched between several future continents. It was ripped off of Africa when North America and Greenland pulled away. Then the bloc struck Asia, and all of Asia and Europe pivoted on Iran. As Europe was driven back into the Mediterranean, break mountains formed along the southern portion and in Scandinavia. The final stop raised the Ural Mountains. Again, Alaska apparently began as the tip of an Asian peninsula. Asia's move north swung the peninsula like a whip, pulling out Korea. Japan and Kamchatka were flung off, trailing arc trenches. As Alaska spun away from Asia, it laid out an arc trench with a small eddy from the turbulence. North America was near the end of its run when Alaska hit and merged with it. Again, this view shows the clearest evidence of turbulence in the crust. As the block made up of India, Australia, Southeast Asia, and other islands hit Asia, it shattered, and the crustal wave divided. The pieces were thrown eastward behind the crustal waves. The northern wave pulled the Philippines off of Borneo. Sumatra laid an arc trench behind Australia. As the waves advanced, counterclockwise turbulence in the crust behind the upper end of the lower wave created a downdraft. Australia, and especially New Zealand, were caught in the downdraft. The New Hebrides Hunter Ridge Arc Trench looped behind the wave. The shallow gouge trenches below Australia traced its move east and then down. Fluidized crust, shown in red, flowed like a river with New Zealand and then past it, spreading out like a delta. The looping arc trench ended as a sort of shearing vortex that raised the islands of Fiji. Again, other features in the Pacific, except perhaps the Emperor and Hawaiian chains, probably existed before the event. Most noteworthy is the mid-ocean ridge stretching from the Indian Ocean to North America, which appears to have run over it. This encounter may have extended the depth of the Rocky Mountains. The ridge may be a remnant of a much earlier collision, one that might have produced the Moon and the protocontinent itself. But that is for another day.